Hello everyone and welcome to this webinar about the dissolution of fuel oil sample for ICP-OES analysis. My name is Philippe Deng and I am the product manager at Claisse for fusion application and consumables. During this presentation, you can use the chat box located on the left of your screen to submit your questions at any time. We may have a few minutes at the end of the present to answer the submitted question. However, if we don't have time to answer all of your questions at the end of this presentation, we will make sure to answer you individually in the upcoming days. Fuel oil is one of the main byproducts of the petroleum refining. It serves as fuel oil for ocean liners and cargo ship engines. It is also used in power plants and industrial plants. During the refining process of petroleum to obtain fuel oil, fluid catalytic cracking catalyst is often used to maximize the distillation of hydrocarbons with a high octane rate. Some contaminants such as nickel, iron, vanadium, silica, alumina, sodium, and copper are found in FCC catalysts and are transferred in the fuel oil during the refining process. It is important to find the concentration of these elements because they are adhesive at certain temperature. They cause corrosion on the reheater tube surface of boilers as well as on the combustion chamber and components of fuel oil engines. Corrosion should be avoided as much as possible because it causes wear and entails additional costs for maintenance or replacement. Different standard test methods are proposed for the fuel oil analysis. In North America, the reference is mainly the ASTM D51N4, so the standard test methods for determination of aluminum and silicon in fuel oils by hashing, fusion, and inductively coupled plasma with atomic emission spectroscopy or atomic absorption. This standard test method proposed to hash the sample to get rid of the organic matter first. Then, in order to dissolve the inorganic material, either use manual borate fusion with a mixture of 90% lithium tetraborate and 10% lithium fluoride flux, or use acid digestion with a solution of chloric acid and tartaric acid. Also, two European standards are well known. The first one, the IP-377, is the equivalent of the ASTM, but with one exception. It doesn't propose atomic absorption analysis. The second one, the IP-501, is similar to the ASTM and IP-377, but the list of elements of interest to analyze is more exhaustive. The fuel oil samples that were used were coming from an ASTM proficiency testing. You can see here the concentration range in milligram per kilogram for each element of interest. You can see that the samples can contain a high concentration of silicon and aluminum. That makes the ashes of such samples hard to dissolve with regular acid digestion. For fuel oil sample, a pretreatment must be made prior to the dissolution or sample preparation. As per ASTM D51N4, the samples were heated at 60 Celsius degrees before being mechanically homogenized for 5 minutes. Then, approximately 18 grams of the fuel oil was weighed in a platinum gold crucible. In order to remove the organic combustible material, the sample had to be burned with an open flame until the sample had lost more than 80% of its original weight. Then, the carbon residue was ignited in a muffle furnace at 550 Celsius degrees. In the table, you can see the mass loss for the burning and hashing steps for each sample. Here's just a reminder of sample preparation by borate fusion. If you want to do a borate fusion, you must weigh your sample in a platinum gold crucible in which you add the borate flux. The borate flux can be lithium tetraborate, lithium metaborate, or a mixture of both. Also, you might need to add an additive such as a non-wetting agent, usually lithium bromide or lithium iodide. You heat up that mixture to melt the borate flux and have the sample dissolve into it. Now, once your sample is dissolved into the molten borate flux, you have two options. You either pour your mixture into a platinum gold casting mold to have a glass disc to be analyzed by XRF, or you pour your hot melt in the diluted acid solution. Then the diluted acid is volumetrically adjusted to get the same acid concentration as used as on the ICP. Now back to the fuel oil sample preparation. Once the sample had been pretreated, it can be dissolved by using borate fusion. In the platinum gold crucible, 0.4 gram of lithium metaborate prefused with 1.5% lithium bromide was added to the remaining ashed sample instead of the lithium tetraborate and lithium fluoride mixture proposed by standard procedure. We use the lithium metaborite lithium bromide flux because silica and alumina have a higher dissolution capacity in lithium metaborite than in lithium tetraborate. Also, the Claisse perfused lithium borate flux allows the complete pouring of the sample during the automated fusion process, thus helping to save time. Also, very important, this flux doesn't contain fluoride, which is making it safer because there is no production of hydrofluoric acid. It is also safer because there is no fluoride, so there is no reaction between fluoride and silica to produce tetrafluorosilicate, which is volatile. So, with the use of lithium metaborate and lithium bromide, you avoid the loss of silica by volatilization. In order to prepare the sample by borate fusion, a Claisse LeNeo electric fluxer was used. This single-position instrument is heated by electric resistance and it can prepare one sample at a time. Like all Claisse fusion instruments, LeNeo is fully automated, safe, and simple to operate. The fusion method used is shown in the table on that slide. The total duration of the method, including the dissolution of the sample, was 13 minutes. Also, the sample was dissolved into a 10% hydrochloric solution. So, this method has the advantages of using only diluted acid solution in order to dissolve silica, alumina, and all the other elements. Once the sample was dissolved, it was poured into a volumetric flask in order to complete the dilution with precision. The final volume of the sample was brought up to 100 milliliters. This slide shows the dilution calculation of the original sample. Once the clear acidic solution is completed, we can start the ICP-OES analysis. Of course, the parameters and the instruments have to be adapted to the high total of dissolved salt and high alkaline concentration. We use the Perkin-Elmer Optima 7300 dual view. The introduction system used was a gem-tip crossflow nebulizer mounted on a Scott spray chamber. We use a quartz torch with a 2 mm alumina injector to avoid the buildup on the tip. Radio frequencies were set at the maximum, 1500 watts, to get a robust plasma. The argon flow rate for the plasma was set as 16 liters per minute. The calibration curves were matrix match with the flux concentration contained in the solution. We added internal standards to all the solutions. The internal standards were chosen according to the element of interest for their similar ionization state and ionization potential. Here's a summary of which standards were used and associated with which elements. This table summarizes the wavelengths that were used. Calcium, iron, sodium, and silica have been analyzed by radial view, while all the other elements were analyzed by axial view. The detection limit was calculated on 10 replicates of a diluted sample solution. Also, this table shows the calibration range for each element with the linearity obtained for each calibration curves. The accuracy, expressed by the relative error, has been calculated by comparing the experimental values of element with the values provided by the ASTM proficiency testing. We show here the equation that we used. Based on 10 replicates, the accuracy for silica and alumina are shown here. It is important to note that the value of alumina and silica provided in the sample were outside the specifications provided by the ASTM, so outside of the calibration curves, even though an accuracy of 97% was obtained for silica and from 89 to 99% for alumina. In order to show the effectiveness of the method, recovery and precision were calculated on each element. The recovery was obtained by comparing spike samples before hashing with the experimental values obtained after hashing and fusion. The concentration used for the spiking was around 50% of the initial concentration. All the elements of interest were tested. As you can see on this table, this method shows great recovery with result being between 93 to 107%. To evaluate the precision of this method, we evaluated the replicability and the repeatability. Let's start with the replicability. To calculate the replicability of this method, we use 10 replicates of one sample prepared on the same day. Then, the relative standard deviation was calculated and is shown in this table. So, as you can see, this method shows great replicability with all results being under 3%. So it shows a great precision. The repeatability was evaluated by analyzing 10 replicates of one sample but prepared on 10 different days. Experimental repeatability, noted as RE in this slide, is calculated according to the ASTM E177. So it's 2.77 multiplied the standard deviation obtained on your 10 replicates. The standard repeatability, noted as R standard, was calculated according to the IP501 for each analyte. In order to qualify the repeatability as good, the experimental repeatability must be smaller than the standard repeatability for all elements but within the concentration range. So you can see on this table that the repeatability obtained is excellent, being at least half of the standard expected value, but with two exceptions, Alumina and Silica, because, as stated before, those two elements were at concentration higher than the specification in the ASTM, so higher than the calibration curve. In conclusion, we can see with the result obtained that using a Claisse LeNeo fusion instrument along with a flux made of lithium metaboride with 1.5% lithium bromide provides great accuracy, great recovery, and great precision. It also avoids having to use concentrated hydrochloric acid or tartaric acid or even manual fusion with lithium fluoride, which transform into hydrofluoric acid. So, with the results shown in this presentation, we can confirm that using LeNeo with a Claisse prefused lithium metaboride lithium bromide flux is a perfect and easy way to prepare fuel oil sample analysis in accordance with ASTM D5184 and IP377 and 501 standards. Using Claisse fusion instrument as a sample preparation method for your sample has a lot of benefits. Since it's automatic, there is no need for supervision during the process. Also, because the fusion process is automated, the safety is increased compared to the typical method, as you don't have to manipulate hot vessel or strong acid. Remember that this method allows you to dissolve your sample within 13 minutes. So we can say that this method has a very quick turnaround, leading to a low labor cost and a great repeatability. In addition to the fact that all labware needed for preparation by borate fusion can be reused, it gives you a very fast return on your investment. This completes the webinar on fuel oil sample preparation by automated borate fusion. I believe that we have time for one or two questions. First question, what are the advantages of using a flux made of lithium metaboride lithium bromide instead of the lithium tetraborate lithium fluoride stated in the ASTM? I would say there are many advantages. First, since there is no fluoride in the lithium metaboride lithium bromide prefused Claisse mixture, silica will not react to transform into tetrafluorosilicate, which is a volatile compound. So using the lithium metaboride lithium bromide will help you get 100% recovery of the silica in the sample, thus giving you more accurate result. Also, the lithium metaboride lithium bromide flux is more fluid than lithium tetraborate and lithium fluoride. So the transfer of your melt and sample from the crucible to the diluted acid solution will be easier, and you will have a complete transfer using lithium metaborite and lithium bromide. So because of that, you will obtain a complete transfer, and this will increase your productivity by reducing the dissolution time needed to dissolve your flux and sample into the diluted acid solution. One more question. Can the burning pretreatment of the sample be automatized? For this application, at first, we didn't test that because we didn't want to make too much change in order to be able to compare the both fusion technique. However, we made some tests with an Claisse M4 automated gas fluxer, and so far we obtained good preliminary result for the recovery of all elements, including sodium. However, more tests will have to be made before we are able to provide a sturdy automated burning method. We are now running out of time. Before we leave, we want to thank you for your attention, and we hope you enjoyed this Claisse webinar. There are many questions that still remain unanswered, but as we mentioned earlier, we will make sure to answer them in the upcoming days. We will keep you informed about our next webinars through our newsletter and our website. So we wish you a very good day, and once again, thank you very much.